Acid derivatives. Let's get started, guys. Do you have a handout? Handout?
The cell phone. I've never.
Remember, if you have any questions about IR, please ask on Monday. IR handout. Acid derivatives, interconversion. Camera. Okay, we've been doing some of this. We're finishing up anhydrides right now. Anhydrides can be converted to esters, amides. At least for what we're doing right now. Let's finish up there. Back over here. And I think we had a couple to predict product on. Okay, we have this, what do we call this? Metachloroaniline, 3-chloroaniline. Reacting with this, it looks like a mixed anhydride. Did we do that one already?
Yeah, we did the top.
Looks like we did, yeah, we did that one. We need to do this one here.
Yes.
We have 2 carbonyls. Carbonyls can get attacked by nucleophiles. What do we have here? Electrophile and nucleophiles. Ether is not going to do much. I mean, it does have lone pairs, but this guy does also have lone pairs. Nitrogen is more nucleophilic, right? Lets this lone pair get out there and get in trouble. These electrons, which carbonyl do we want to attack?
Left.
Right. Let's see, this has an sp3 carbon that donates. This has an oxygen. What does it do when it can do both? Because it can do both here. It can donate by resonance and withdraw inductively. Just like with aromatics, the net effect of oxygen when it can do both is
Withdraw.
no. EAS, it's group 1.
Donate.
Net effect is activator. Okay? When oxygen can donate and would donate by resonance, withdraw inductively, it donates by resonance more. And this is inductive. sp3. Resonance donation is going to be stronger. Okay, so which carbon is more partial plus, left or right? The one on the right is more partial plus compared to the one on the left. So there's more partial plus there. These electrons add here, electrons up. Okay. Let's go ahead and do it stepwise. Okay, we have N and O. There's an H there. Nitrogen is now bonded to that carbon. Electrons up. Minus what's on that carbon? A methyl and an oxygen. The oxygen is bound to a carbonyl O-ethyl. Plus, minus. Everybody agree that's what we get when this does a nucleophilic addition to the carbonyl on the right? Yeah? Okay. We can do proton transfer. Okay. Strictly that might be correct. I'm just going to come back down and kick off the leading group. What does that give? O, N, H. This is bonded to a carbon that's double bonded to oxygen now when the electrons came back down. What else is on this carbon? Methyl. Plus charge. What was the leaving group? Acetate, right? That's acetate. Oh, I'm sorry, it's not acetate. We have an O-ethyl, yes. Not acetate. O-ethyl. This is interesting. To go neutral here, this could take the H. Yeah, you could do that, but then you're going to have an acid here. Triflamine can take the H from this Or you can go ahead and just have triethylamine take the H from this, leave that behind. In the end, the final product here, I'll draw it here, is nitrogen has just a what do we put on the nitrogen? Terminology.
Acyl.
It's an acyl. Acyl is kind of a generic term. It's an acyl with a methyl. What do you call that? It's kind of strictly an acyl, but usually acyl is any size. That's an amide, right? It's an amide. If that was an OH, that would be what?
Carboxylic acid.
What carboxylic acid? Methyl carbonyl OH? Acetic acid. Might recommend watching the nomenclature video. What do you call an amide of acetic acid? Acetamide. Acetamide, yeah. We made the acetamide of, this is morpholine. Morpholine, that's just the common name of that guy. You don't need to know that. Occasionally you'll see some drugs that have the morpholine ring. Okay, we made an acetamide. Instead of using acetyl chloride or acetic anhydride, we use it. That would probably never hardly be used to make acetamides. I just use it in my example. But actually, things like this are very selective. You might not think there's much difference in the carbonyls, but this and this, there's a huge difference. Very selective for there. This is very selective for there. So those are some mixed anhydrides and how you predict which carbonyl to attack. We use our same ideas of electronics, donation, resonance, etc. Same stuff we've been using since middle of Organic 1, or really earlier. Phosphoric acid. This is just an application here. We're finishing up in hydrides. Anybody ever heard of pyrophosphate?
Yes.
Pyrophosphate is used a good bit in biochemistry, both in actual biochemistry in your body, also in biochemistry lecture. Okay? What is pyrophosphate? Well, it's just the tetraanion of pyrophosphoric acid. What is pyrophosphoric acid? It is actually the anhydride of phosphoric acid. Because if you take two of these and combine them and remove water, you get that. And you see how it has an oxygen between the two sort of, they're not carbonyls, but they're P-double-O's. Okay? Sort of like an anhydride. It's the anhydride of phosphoric acid. It's called pyrophosphoric acid. What does pyro mean?
Fire.
Somebody said heat, hot, heat. Fire, okay? You take this and you put it in the fire, and you heat it up, and it'll real hot, and you can thermally get it to drive off water. And you get this, and they said, oh, we'll call it pyrophosphoric acid, because we just pyrolyzed it, we heated it. But then all these H's here, so acetic anhydride doesn't have any acetic H's. But this anhydride's got 4. And they are all acidic, and it can exist like that in the body. And that's called pyrophosphate, and it's used a good bit in your biochemistry. So it's actually the anhydride. Now you might say, well, doesn't the body have a lot of water? How can an anhydride exist in the body? Well, that'd be a good question, because you add water to this, you're going to go back to that. I imagine this is probably not that of a reactive of an anhydride. It's not as reactive as acetic anhydride. So that's probably how it can survive in the body, and where acetic anhydride probably would never even survive in the body. And acetyl chloride, definitely not. Okay, so that's just a little application of the idea of anhydrides. Any questions about anhydrides? Acetic anhydride. Okay, buy a jug of it, pretty cheap. You know, acetic anhydride is one of the biggest chemicals on the black market. And actually this year, back in January, I saw a news story where some country seized like huge millions of liters of it. It's the biggest seizure of acetic anhydride ever. On Monday, I want someone to tell me why acetic anhydride is big on the black market. Okay? Very specifically why. That is, if you tell me your answer, I want you to anticipate what question will I then ask you in response. You should always be doing that, right? Let's practice that. Why is Bill Gates rich? I mean,
Because he has money.
okay, that's right. Why is Bill Gates rich? Because he has lots of money. That's not really the answer, though. So let me ask you again. Why does he have a lot of money? Okay. So you got to, there's layers of answers. So you got an answer in your mind. Anticipate. What is the question going to be after I tell my answer? Then you can refine your answer and you can get a better answer, right? Be prepared for that second question. Yeah? Good. Chemistry of esters. Esters. Have we ever synthesized esters? Well, yes, we've done it twice. Look back at section 2B and 3B. One of the most common ways to synthesize an ester is the Fischer esterification. Fischer esterification, probably one of the top 10 reactions in organic chemistry. Okay? There's about 20, 30 of those. Usually those have names, they're named after chemists. Fischer, Grignard, Wittig, although we haven't covered Wittig yet. Williamson. Suzuki, we won't cover it here, we'll do it in the lab. Et cetera, et cetera. Okay. What can you do with esters? Well, of course, you could look at the here, and we're at esters. You can only convert an ester to a less reactive derivative, so you can only convert it to an amide directly, right? Or, as stated on the table, any acid derivative can be converted back to the carboxylic acid, which is at the top, by reaction with water. Water and acid, which is H3O+, or aqueous base, which is hydroxide. Now, of course, if you make an acid with aqueous base, how is it going to exist? Basic form. If you did a sweater in a pool, it's going to be wet. So if you want to get it back to the actual acid, you have to then treat the carboxylate with some type of strong acid. Okay? So this is hopefully organized in a way that you should be recognizing and hopefully learning this stuff. Okay. So, what can we do with esters? Well, the first thing I want to show is hydrolysis back to the carboxylic acid. Now, it requires more than water. Acid chlorides and anhydrides will react with pure water. When you get to esters, they're less reactive. We talked about why. And they actually do not react with pure water. So esters you find in nature all the time. You find esters in fruits. Okay? Perfume. A lot of esters are sort of aromatic. Now, when I say aromatic, that doesn't mean chemically aromatic. That means sort of fragrant. So fragrant is probably a better word, not aromatic. Question?
Are esters the general things that smell good?
Esters?
Yeah.
There's one handout in here where there's actually a lab. I've never done it. There's a lab where you make a variety of esters, and each one has a different fruit smell. And so you can be assigned raspberry, and you can be assigned banana. Oh, we do that one? Yes. It's too fun. Scratch and sniff stuff, where you scratch it and you sniff it. You know, like in second grade? Usually those are esters that are just sort of underneath the
So that stuff that you have to make smells good, does it cost a lot? That's why, is that why?
It can cause too much stress on everything.
In the green pack, there's a list of esters. They're pretty small molecule esters in raspberry, pear, apple, pineapple, etc. Okay. A lot of esters are used in your perfumes. They're fragrant. Small molecule esters. Larry.
I'm looking at some of the names there. They seem kind of peculiar, like the third one down, the fourth one down. Is that methyl? Is that the same thing as methyl butanoate?
Yes, butyrate, that's kind of a slang ending. Let's practice nomenclature. You watched the video?
I did.
Very good. Name this compound here. I see what looks like an ester. That's the carboxylic acid portion. 1, 2, 3, 4. So that's not butane, but
Butanoate.
well, it's butanoic acid. But since it's an ester, it's going to be butanoate. What's the R group?
Methyl.
Methyl butanoate. Methyl butyrate. It's sort of a slang.
Is it something the Brits came up with?
I don't know where some of the slang comes from. In organic 1, we used T-amyl alcohol. Amyl is slang for 5 carbons. There's lots of slang around. I don't know where it comes from. Butyrate, yeah. Acetate is not really slang. Acetate is so common that it's common. Butyrate's a little slang. Propionate, propanoate, yeah. It's a little confusing. You have to ask. Somewhere along the line, chemists just wanted to be a little tricky or have a different name or something. Maybe it's in British English or something. I don't know.
There's more standardization in chemistry than there is in physics.
Okay. There you go. Okay, esters. Let's look at what can you do with esters. One thing you can do is hydrolyze them back. Hydrolyze them back to the carboxylic acid. Any acid derivative can be hydrolyzed. Okay, you can either use aqueous acid or aqueous base. Can't react with just pure water. For example, aqueous acid. Take this ester. Probably going to have to heat it up. Maybe not. Not that important. It's the acid plus what? It's going to be coming off as ethanol. This is the reverse of what? And if you come this way, it's the Fischer esterification, where we took an acid and a small alcohol, we came this way, made this plus water. I'm not going to do this mechanism. It's just the reverse of the Fischer esterification. You need to sit down, do the Fischer esterification, and then look at it in reverse. Write it out in reverse. We talked about how do you drive the Fischer esterification. If you come this way, you make this plus what?
Water.
Water. If you're over here, how do you drive it that way? Remove the water as it's formed. What's another way you can do? We talked about using a large amount of ethanol, small alcohol, drive it that way. We talked about how you don't want to use a large amount of that because that's really not driving it. If you increase the amount of that, it doesn't change the, okay, remember when I did it 50-50, whatever. But you can use a large amount of that, and at the end you just remove this so like on the rotor valve. Okay? Well, if you're over here, how do you drive this that way?
Remove ethanol.
If you remove ethanol, you could. In practice, though, it's more common to do the other thing. How else would you do this?
Add water.
Yes. So you're adding water to that to go that way. What you would do is you would use just a lot of aqueous acid, a lot of water. And that'll drive it this way, and you'll be all right. Okay, so add water, drive it the other way. So you need to look at the Fischer esterification. There's both ways. The reverse is called hydrolysis, back to the carboxylic acid. We're under acidic conditions. So in terms of what is the mechanism, first step you would do going to the right. Protonate the carbonyl. When you do carbonyl chemistry under acidic conditions, the first thing you always want to do is protonate the carbonyl. We'll do that the rest of the semester, especially with aldehydes and ketones. Okay, you can also hydrolyze an ester using base. Now this probably also requires water. Actually, it does require water, and so it's not just hydroxide. Let's do this mechanism. Let's see if it really requires water or just hydroxide or what. Let's see. Okay, H plus work up. We have to first finish step one before that comes in. You can't mix acid, base with acid. It's two separate steps. Okay, we got hydroxide. What's the first step? Do we protonate carbonyl? No, we're not under acidic conditions. We're under basic conditions. So what's the first step?
Abstract the methyl.
Abstract the methyl,
Extract the methyl.
make the carboxylate
How do you want to extract the methyl? This is actually a good point. Do we want to do this and kick off the oxygen?
if we could.
Would that give these products? That would make O minus, you protonate it? That actually would give the products. But the mechanism is not, what type of mechanism would you call it? Looks like an SN2, right? Like carbon leaving group. That is reasonable, but this is not how hydrolysis of an ester occurs. Because if you star this oxygen, that's that oxygen there. With esters, in forming them or breaking them, you never break the OR bond. Okay. So it's not that. Oxygen is not a great leaving group. You might say, well, it's going to be stabilized, almost like a tosylate. Just no good. Reasonable, but no good.
So you gotta attack that carbon.
We attack the carbonyl. Electrons up. Nucleophilic addition to the carbonyl. What do you want to do next?
Make a double bond.
If we transfer a proton, it would be the same structure. We'd have an OH and an O minus. So there's no need to do a proton transfer. Next step is electrons come back down. Which is a better leaving group, O methyl or OH? You might say an OH because the methyl donates the oxygen. They're actually very similar. If we kicked off the O, we'd just be going backwards. To get to where we're going to kick off this here. So we reform carbonyl, and we get OH plus what? That's the LG. Now this is a plain oxygen. Can a plain oxygen be a leaving group?
No.
Not for SN1, SN2, etc. But what are we doing? Anytime you make a pi bond, kick off a leaving group, that's easy to do. We'll see lots of things leave, even carbon sometimes. Okay? Because the nucleophilic addition is your slow step. This is a fast step. Note that I did not do a proton transfer. Is this an acidic proton? Kinda, I mean, it's an OH, but it's not a strong acid proton. Only time you do proton transfers is when you have an H that's on a positive atom. And you transfer it. It's like you have a hot potato acidic H. You're not going to transfer this H. You typically do proton transfers when you're under acidic conditions, or the chemistry just leads to a H on a positive atom, which then looks like it's acidic. This is not acidic. That looks like an alcohol. Are alcohols acids?
No.
You don't call them acids. Or
So, like, in this case, like, the hydroxide will never, like, take the H. I mean, actually, no, you're assuming it does, right? And then that's the...
take which H?
The alcohol H.
That's just not acidic enough. I mean, you could show it, but it's not a good equilibrium.
Well, why is there H plus work out?
We haven't got there yet.
Okay.
Because this is not in step one.
We made it in a pool.
Yes, this is the base.
Oh.
That's an acid. Are you going to say, okay, what's your form? I don't want you to take this H. It won't listen to you. This will take the H, leave that behind, and you get what?
Carboxylate anion.
You get the carboxylate plus what? Methanol, which we said we're going to form. This is in step one. We're under basic conditions. If you make an acidic product under basic conditions, how is it going to exist? Basic form. To put the proton on, what are we going to have to add? You're going to have to add your favorite strong acid, which is what, Warren? HCl. Good, we got lots of that already. HCl will protonate it. What sets with this O minus if you want to show sort of a full balanced? Same thing that's set with this OH minus. Sodium. There's a sodium plus there, but it's a spectator ion, because I didn't show it. At the very end, you're going to have sodium chloride. Strong acid is going to protonate anything, especially any base, any anion. If you don't believe me, consider your pKa's of each side, and
So to drive this forward, would you just boil off the methanol?
do what?
To drive this forward, would you just boil off the methanol?
You don't really need to drive this forward, because at this point, it's not reversible. Why is it not reversible? Because this is a carboxylate, and nucleophiles do not attack carboxylates. Remember, game over? Wah, 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 wah. Okay? Carboxylates are unreactive towards nucleophiles. You look on this sheet here, look down here. Least reactive species toward nucleophilic addition, carboxylate, and actually when I said that, I told you that nucleophiles do not add. Game over. Right? So that's why you don't need to drive it. It comes to a point where it won't reverse. Did we need water there or not? Did we ever have to bring in a water molecule?
No. Well, yeah, HCl's aqueous.
Well, HCl doesn't have to be aqueous.
Anyway,
Okay, it doesn't look like it needs water, but you're going to have to use water. Why? Because sodium hydroxide is not really soluble in anything functional. I thought maybe it needed water somewhere. Maybe it's another reaction that you also need. You need base and water. Apparently it didn't need water. We never used just a plain water molecule. Okay. Just show the product of the next reaction. Okay? Mechanism you should know, but you also have to just be able to quickly predict products. All right? It's a combination of some memorization, but also mechanistic thinking. What's the functional group I'm reacting here? But ester? It's a little bit odd because the acid portion is actually the small portion. This is a big ester of acetic acid. Now it's got an aromatic ring. So we know aromatic chemistry, we know this sort of carbonyl chemistry. So H3O plus, does that seem like an aromatic ring reaction?
No.
No, I mean, what's the electrophile here if you consider it an electrophile? It's final exam time, guys. What's the electrophile here? H plus. The ring can react with H plus and add an H, but it's not going to do anything new though, okay? So there's no ring chemistry here. Well, can aqueous acid do anything to an ester?
Yeah.
Hydrolysis of an ester. What I'm getting at is you have to, as we move forward, there's going to be more and more possibilities. You've got to assess what's going on, assess the chemistry that we can do. This is hydrolysis of the ester. Show the products. If you want to work it mechanistically, fine. You can just do a quick mechanism. This has here, this lead. Usually you want to show everything neutral at the end. That alcohol plus acetic acid. If you don't readily see that, you need to sit down this weekend and just do it mechanistically and see. It's like math. If you don't believe that 50 times 50 is 3,025, sit down. Sorry, 50 times 50 times 50. 3,025, that right? Yeah. Sit down and make sure you understand why it's 3,025. Okay? Do it.
It's 2,500. It's 2,500 if it's 50 times 50.
You get your point.
that.
Huh?
The O double bond becomes the OH.
To begin.
The O is double bonded currently. It's the one that ends up the OH in the carboxylic acid.
This becomes OH.
No, the other one. That one. The other OH.
What happens is this is open.
It picks up the H, right?
In the mechanism?
Yeah.
First step of this mechanism is protonating the carbonyl. Carbonyl chemistry, the first, under acidic conditions, first step is always protonating carbonyl. This is the reverse of Fischer esterification. Yeah. Okay. Go back to the acidic hydrolysis, I mean not acidic, but basic hydrolysis. Basic hydrolysis. Basic hydrolysis of an ester is typically known as saponification. Saponification. What does saponification mean? Soap forming. Soap forming. Why is it called saponification? Well, if you take the triglyceride, what is a triglyceride? It's the triester. See, that's an ester, ester, ester. This is a CH2, this is carbon, 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 okay? It's the triester of what?
Glycerol.
Glycerol, yes. Glycerol is this 3-carbon triol called glycerol. If you make each one of these into a carbonyl, an R group, ester, 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 you get a triglyceride. Okay? It's actually a triester. Well, what happens if you take an ester and heat it with aqueous base? Hydrolysis of the ester. And if you hydrolyze this, what are you going to get? Hydroxide adds electrons up, back down, kicks that off, kicks that off, kicks that off.
Trial.
You're going to get glycerol plus what?
3 long-chain carboxylic acids.
You're going to get the carboxylic acid, and you get 3 equivalents. How do you make an ester? Acid and alcohol gives ester. This is going to be in the basic form because we're under basic conditions. What do you call this long-chain fatty acid? Well, that's what you call it. It's a long-chain fatty acid.
That
Okay?
wasn't open paper video.
With this chain being like about 18 carbons long, just hydrocarbon. Fatty acid. And what is this? That is typically soap. Okay? If you look at your shampoo, but it has a label on it. Usually your soap bar doesn't have a label on it. Next time you take a shower, this weekend or next weekend, look at your shampoo. The first ingredient is going to be something like sodium myristate or sodium palmitate. Okay? It's just a long-chain fatty acid. So this is how people used to make soap. They take triglyceride, heat it with base, and this, even though it's ionic, is not that soluble in water. It's got some solubility, but not a lot, because it's got so many carbons, like 18, that it keeps it from being highly soluble in water, even though it's ionic. You might believe that. If you put a bar of soap in the water, does it quickly dissolve? No, eventually it'll fade away, but it's not going to quickly dissolve. Okay? Now, so they made this back in the Pioneer age, and they figured out that you could take this stuff and you could bathe with it. Why is it good for washing?
It's antipathic.
What?
It's antipathic.
Antipathic?
Or antipathic, isn't it? Like, it's got polar and non-polar regions. So
Has a polar region,
Oh.
with water in it.
maybe I said the wrong order.
I don't think it's antipathic.
No, not
Amphoteric.
amphoteric. Okay.
Amphoteric. Yes, that's why. But why does that make it good for bathing?
Because it's got a long non-polar chain to dissolve any non-polar like grease or anything. It's got a
Yes.
head with proteins.
It's good for removing oils from your body, not just mechanical dirt, but oils, okay? Because we bathe with water, not acetone. And oils are not that soluble in water. So how does this help solubilize the oils? It's got dual character. The long hydrocarbon portion sort of associates with the oils, but the polar head group associates with the water. And so it can bring the water and the oils together and rinse them down the drain. Sort of like an arbitrator. Okay? And actually, back in Organic 1, I gave you a handout where we were talking about physical properties, and it talked about this. In terms of like lipophilic and hydrophilic character, What type of character does a side chain have? Lipophilic. It loves lipids, fat loving. What type of character does the head group have? Hydrophilic. It loves water. Okay? So it sort of brings the grease and the water together. Now if you bathe with acetone, then you don't need that. The acetone will just wash off the oil. Okay. So how did they make that in the old days? How did the pioneers make that? You ever watch Beverly Hillbillies?
Yeah.
You do? What did Granny make in the backyard? She had a big black kettle and she would stir it up. She'd make soap. Okay, how'd she make soap? Right here.
What was the name of these?
Where'd she get the triglyceride from? Possum fat. Okay, take a dead possum, take the fat. Okay, that's where you get fat. When we say fat, it's a lot of things, but it's largely a lot of triglycerides. So she took possum fat, put it in the kettle with some water. Where'd she get the base from? Did she call the chemical company and get the base? Where'd she get the base from? Fireplace ashes. Because fireplace ashes have a large amount of what? Carbonate. Carbonate, like sodium carbonate. Because under that high heat, water will react with CO2 to make carbonic acid, but then apparently it becomes basic somehow and you remove the H's. Carbonate, but you put carbonate in water, you get base. Okay? So possum fat, fireplace ashes, water, heat it up. What would happen is this stuff, when it was formed, would float to the top, like soap floating. Should scoop it up, put it into some molds, and let it cool and harden, and then here's your bar of soap. All right. So Granny was doing chemistry in the backyard. Y'all don't even know what we're talking about. I know, and I don't know why you watching Beverly. See, when I was growing up, it was Beverly Hillbillies, Andy Griffith, and the Atlanta Braves every night. WTVN. Okay, so that's saponification. All right. What if we hydrolyze? What is a lactone? A cyclic ester is known as a lactone. What we got here? If you hydrolyze a lactone, which is what we're doing here, what do you get? Can you show the product of that hydrolysis of that lactone? All right. Let's see what we got here. Hopefully you work mechanistically. If you don't have time, you can work on that. How does that look? I'm just going to do it kind of quick to kind of, okay. That adds electrons up, then the electrons come back down and kick off what? Kick off the oxygen. This O will then take the H from this. And at the end of step 1, you'll have the minus here. H plus work up puts on the H. Okay? I'm not taking the time to go through this every time. You need to sit down. It's the same old mechanism, and you got to prove to yourself that this is the product. And say, hey, how can I quickly just know this and just think mechanistically? That's hydrolysis of a cyclic ester, known as a lactone. There's, in one of the handouts, there's the green. You've heard of erythromycin? Of course you have. Erythromycin is called a macrolide. Macro meaning large. The lide ending refers to a large ring. In the middle here, this is a large ring. It's about 16 atoms big, this big ring. But part of the ring is right here. Oh, okay, see this ester? It's actually a cyclic ester, which is a lactone. Versus azithromycin. You can read the question there. Think about that. What can you do with esters other than hydrolyze them? You can convert them to amides, because amides is a less reactive derivative. For example, you can react this ester with this amine. You can get the amide plus ethanol. You can do this mechanism on your own. It's the same old thing. Nucleophilic addition, you may do a proton transfer, etc., etc. If you want me to look at it, I can. But this is typically not the best way to make an amide. If you want to make it this amide, using this amine, instead of reacting with the ester, what would you react it with instead?
Acid chloride.
Acid chloride. Because the ester is not that as reactive. This is probably going to require a good amount of heat. You'd rather use an acid chloride or the anhydride. But you can do it with an ester. Okay, chemistry of amides. Also known long-term as carboxamides, because it's a carbonyl amide. We've already made amides from acid chlorides and hydrides. We've even made it from esters, which we just did. So you need to look back at that. Of course, you can hydrolyze an amide, because any acid derivative can be hydrolyzed back to the carboxylic acid. So if you take this primary amide here, treat it with aqueous acid, you can hydrolyze it back to the carboxylic acid plus ammonium. What's the first step of this mechanism? Protonate carbonyl. Anytime you're under acidic conditions doing carbonyl chemistry, first step is to protonate carbonyl. Protonating the carbonyl makes the carbonyl more electrophilic. Because this oxygen is now pulling greater, making this carbon more partial plus. Now what nucleophile adds to carbonyl? Water. Hydrolysis. We're going to lyse it with water. So we add the carbonyl, we push the electrons up, give the oxygen what it wants. We get to that point there, yeah? What do you propose doing next? Ultimately, what do we got to eliminate off of this carbon? Nitrogen. Which is a better leaving group? Neutral nitrogen or protonated oxygen? Yeah. We look like we want to do a proton transfer. Move the acidic proton to the nitrogen. I'll come way over here. Proton transfer, we're not going to use a mechanism arrow. Move the hot potato over to the nitrogen. We left the lone pair behind, okay? At this point, the two OHs are equivalent. You can use either one to do the next step. I'll use the top one. Now the electrons down kick off the ammonia, and that will give the acid plus what? Plus NH3 neutral.
You lost the D.
Oh, I have. Oh, yes, very good. Yeah, rookie mistake. There's an H here. Okay, what do you want to do next? Water can take the H and you could reform your H plus catalyst. In the end, though, ammonia is basic. How's the base going to exist under acidic conditions? This is a case where we made a basic product. This you're going to show taking the H. Wherever you want to take the H, this is going to have it at the end because that's a base. And when that takes the H, what do you get? You get the two products shown. Okay? Ammonia is a base. Under acidic conditions, it's going to exist as the protated form. Okay, you can hydrolyze it with base below. Please look ahead. We'll probably on Monday get you the yellow sheet. Okay? Which does include some aldehyde ketone chemistry. Have a good Friday, guys. See some of you in lab.
I knew it, that we should say. I did.